Welcome back, design junkies, to Mechanical Engineering Made Simple. If you enjoy the podcast, show your support with a like, a follow, or a comment. So I want you to imagine being a soldier on a 19th century battlefield.
Okay, setting the scene. I like it.
Right. So you're there, and suddenly you hear this deafening, explosive crack of a bullet striking the earth literally right next to you.
Terrifying.
Yeah, completely. But here's the crazy part. A moment later, you hear the distant sound of the actual rifle that fired it.
Ah, yes. The bullet physically arrived before the sound of the gunshot.
Exactly. It's wild to think about. Or picture this. You're trying to design a modern commercial airliner, right?
Yeah.
Like a 400-ton Leviathan of the skies.
A massive engineering undertaking.
Huge. And you realize that the only way to calculate how it will actually fly is to use imaginary numbers. I mean, numbers that literally do not exist on any physical number line.
It sounds like science fiction, honestly,
Yeah.
or perhaps magic. But it is the absolute foundation of the modern world.
It really is. And today we are embarking on what I'm calling a masterclass.
I think that's the perfect word for it.
Yeah, because if you have ever looked out the window of a commercial flight and wondered, how the air is actually holding you up.
Right. Or if you've ever just watched water flow around a rock in a stream and wondered if that chaotic movement could be perfectly predicted.
Exactly. This conversation is going to fundamentally change the way you see the invisible forces around you. We are going to completely decode fluid dynamics today.
It's a massive topic, but so incredibly fascinating.
It is. And we're breaking this deep dive down into 3 distinct phases. First, we're going to explore how engineers scale reality.
Which is way harder than it sounds.
Oh, absolutely. Because if you want to build a brand new jetliner or a revolutionary car design, you can't just build a full-size prototype out of the gate. We have to look at how we shrink the physical world without, breaking the laws of physics.
Right. And then second, we're going to look at the ingenious, almost mind-bending tools engineers use to measure the invisible.
Like how we actually track the movement of air and water when you can't even see it.
Exactly. And finally, we will dive into the pure, elegant mathematics of flight. We'll explore how theoretical, impossible fluids and abstract geometry miraculously dictate the reality of lift.
It is a phenomenal progression. I mean, we are going to travel from incredibly practical, gritty, engineering challenges.
Including a genuine medical mystery from the Franco-Prussian War, which is a great story.
Yes, I can't wait to get to that. All the way to the breathtakingly abstract mathematics that literally govern our physical universe.
It's going to be quite the journey.
Okay, so let's unpack this. Phase 1. Dimensional analysis and the law of similarity. Or, as I think of it, the incredible headache of scaling reality.
That is a very accurate title for it.
Right. So let's ground this right away. Suppose you were designing a brand new, highly aerodynamic electric vehicle.
Okay, an EV. Got it.
And you want to test the aerodynamic drag. But building a full-size functioning prototype is prohibitively expensive.
So naturally, you decide to build a 1 to 10 scale model of the car and put it in a small wind tunnel.
Which is the logical, intuitive approach. Everybody does that, right?
They try to, but fluid dynamics is rarely intuitive.
Yeah.
I mean, the instinctive thought is that you can just take the physical geometry of the car, shrink every single dimension by a factor of 10, blow wind over it, and then just scale your results back up.
But the universe absolutely refuses to let you do that.
It flat out says no.
I always compare this dilemma to baking. If you are listening to this right now and you've ever baked, you know this exact pain.
Oh, the baking analogy is perfect for this.
Right. Let's say you have a family recipe for a standard-sized cupcake, and it is just flawless.
Delicious.
And you decide you want to bake a giant wedding cake-sized version of this exact cupcake. You can't just multiply all the ingredients by 10, pour it into a massive pan, and bake it at the exact same temperature for 10 times as long.
You would end up with a complete disaster.
Exactly. You'd end up with a cake that is entirely incinerated on the outside and like a raw, soupy liquid on the inside.
Because the physics of heat transfer scale differently based on the ratio of volume to surface area.
Yeah. The thermal mass completely changes. And the same exact logic applies to fluids like air and water. Just shrinking the physical shape of the car isn't enough.
No, it's not.
Ooh.
We need to achieve what engineers call dynamical similarity.
Dynamical similarity. Okay, break that down for us.
Well, the baking analogy is brilliant because it highlights that geometry is only one piece of the puzzle. To achieve dynamical similarity, meaning the fluid behaves exactly the same way around the small model as it does around the prototype, engineers have to use a mathematical framework called dimensional analysis.
And dimensional analysis has some pretty strict rules, right?
Very strict. The absolute bedrock rule of dimensional analysis is that any equation that describes a physical reality must be dimensionally consistent.
Meaning you cannot add mass to time.
Precisely. You cannot add 2 kilograms to 5 seconds. It is a meaningless sentence in the language of physics.
It's like adding apples and Tuesday. It just doesn't compute.
Exactly. You can multiply them, sure, or you can divide them, but you absolutely cannot add or subtract them. Every term in a valid physics equation must ultimately boil down to the exact same fundamental dimensions.
Okay, so how does that help us scale our car?
By utilizing this strict rule, engineers can take incredibly complex, chaotic, messy problems and reduce them into much simpler, non-dimensional groups.
And the key to this is a mathematical magic trick, right? Buckingham's pi theorem.
Yes, Buckingham's pi theorem.
I want to spend some time on this because when you first encounter Buckingham's pi theorem, it literally feels like a cheat code for the universe. How does it actually work?
It is incredibly elegant. Basically, the theorem states that if a physical phenomenon is influenced by a certain number of physical variables, let's call that total number n.
Okay, so n is the number of variables.
Right, and those variables can be described using a certain number of basic fundamental dimensions like length, mass, and time. We will call that number k.
So k is the basic dimensions: length, mass, time.
Exactly. Then the entire complex phenomenon can be mathematically expressed by exactly n minus k non-dimensional groups.
Okay, we need to map this onto something real so people can visualize it.
Okay.
Let's take the classic example of calculating the aerodynamic drag on a sphere moving through a uniform flow of fluid.
Like a baseball flying through the air.
Yeah, baseball, or a submarine dropping deep into the ocean.
Perfect. Let's list every single physical variable that dictates how much drag force that sphere experiences.
Okay, let's do it.
We will call the drag force capital D. That's our first variable. Now, what else matters?
Well, the physical size of the sphere definitely matters. So we have its diameter.
That's 2. The speed at which it is moving matters. So we have flow velocity. That's 3.
The heaviness of the fluid matters too. So we have fluid density, 4.
And finally, the stickiness or internal friction of the fluid matters, which is the fluid viscosity. That makes 5.
So counting them up: drag force, diameter, velocity, density, and viscosity. That is 5 total variables governing this scenario. Our n equals 5.
Exactly. Now, how many basic fundamental dimensions do we need to describe those 5 variables?
Let's see. We need length to describe the diameter, obviously.
Right. We need mass to help describe the density.
And we need time to help describe velocity, because velocity is just length divided by time.
Spot on. So our basic dimensions are length, mass, and time. Our k equals 3.
And here is where the Buckingham pi theorem steps in. We take our 5 variables, we subtract our 3 basic dimensions, and the theorem guarantees that we are left with exactly 2 non-dimensional groups. 5 minus 3 equals 2.
Yes. Through a specific algebraic process, engineers multiply and divide these 5 variables against each other until all the units of mass, length, and time completely cancel out.
It's just so clean. And for the sphere, what are those 2 resulting groups?
They are the drag coefficient and the Reynolds number.
Wow. Okay, think about how powerful this is. Instead of an engineer trying to plot a wildly complex graph with 5 different axes to track all those changing variables.
Which would be impossible to read, by the way.
Right. They only need a single 2-dimensional graph comparing the drag coefficient to the Reynolds number. It simplifies the chaos of reality into a clean, predictable line.
That is just phenomenal. It takes all the noise out of the system.
Let's look at another common engineering problem just to cement this. What about the pressure you lose when you pump a fluid through a long pipe?
Oh, pipe friction is a great example. If you are designing an oil pipeline or a city water grid, you desperately need to know how much pressure you are going to lose due to friction.
Because otherwise you can't size your pumps correctly, right?
Exactly. And for pressure loss in a pipe, you have 6 variables to juggle.
Okay, lay them out for me.
You have the fluid velocity, the pipe diameter, the fluid density, the fluid viscosity, the physical roughness of the inside wall of the pipe, and the actual pressure loss per unit of length. So our n is 6.
Got it. Then we subtract our 3 basic dimensions of mass, length, and time. So 6 minus 3 leaves us with 3 non-dimensional groups.
And those 3 groups turn out to link the friction factor of the pipe to the Reynolds number and the relative roughness of the pipe wall.
That's amazing. We have once again taken 6 messy, interacting, real-world variables and boiled them down to 3 pure, dimensionless relationships.
It's why dimensional analysis is essentially the secret weapon of mechanical engineering.
Okay, so this brings us right back to our electric vehicle scale model. We have our clean, dimensionless relationships. But how do we actually guarantee dynamical similarity between the tiny 1 to 10 scale model sitting in the wind tunnel and the real full-size car cruising down the highway?
Right, the actual physical test. To achieve true dynamical similarity, you have to match the force ratios.
Match the force ratios.
Yes, the ratios of the various physical forces acting on the tiny model must be mathematically identical to the ratios of the forces acting on the giant prototype.
Okay, and the most famous, the absolute king of these force ratios is the Reynolds number, which we just discovered using Buckingham's pi theorem.
It is the absolute king. You cannot do fluid dynamics without the Reynolds number.
Let's define the Reynolds number because, like you said, it is impossible to talk about fluids without it.
Simply put, the Reynolds number is the ratio of inertia force to viscous force.
Inertia being the tendency of the fluid to just keep barreling forward in a straight line.
Exactly. And viscosity is the fluid's internal friction, its thickness, its tendency to stick to itself and to the object moving through it.
Like honey versus water.
Exactly. The Reynolds number tells you which of those two forces is winning the battle. Is the fluid rushing past smoothly because of high inertia? Or is it dragging and sticking because of high viscosity?
And it's crucial for specific types of flows, right?
It is the crucial governing metric for anything that is wholly submerged in a fluid without a free surface.
So a submarine navigating deep underwater.
Yes. Or an airship flying through the sky, or water flowing through a closed municipal pipe system.
But here is where my brain always hits a roadblock, and I think it's the great headache of model testing. Let's just follow the math for a second.
Okay, let's do it.
The formula for the Reynolds number is fluid density times velocity times the characteristic lengths, like the physical length of the car, all divided by the fluid's viscosity.
Oh, that's exactly correct.
Okay, so if we are testing our car model in the exact same air that the real car drives in, the density and the viscosity are exactly the same, right?
It's just normal atmospheric air.
But our model's length is 10 times smaller. So to keep the final Reynolds number mathematically equal between the tiny model and the real car, doesn't the wind speed in the tunnel need to be insanely, impossibly fast?
It absolutely does. This is the brutal, harsh reality of scaling.
I knew it. The math demands it.
Let's put real numbers to it so you can see how crazy it gets. Let's say your full-size prototype car is 3 meters long, and you want to test how it performs at a standard highway cruising speed of 60 kilometers per hour.
Oh, okay, pretty normal scenario.
To match the Reynolds number on a 1 to 10 scale model, which is only 30 centimeters long, the wind velocity inside your testing tunnel has to be blasted at 167 meters per second.
Wait, 167 meters per second. That is over 370 miles per hour.
Exactly. It's a localized hurricane.
But that introduces a completely fatal flaw to the experiment, doesn't it?
It does. Because 167 meters per second gives you a Mach number of 0.49. You are traveling at nearly half the speed of sound.
Wow.
And at that velocity, the air fundamentally changes its behavior. It begins to suffer from compressibility.
Okay, let's explain compressibility. Because air is a gas, it acts kind of like a spring, right?
Exactly like a spring.
At normal, everyday highway speeds, the air simply parts and flows around the car. It acts as if it is incompressible.
Right, it just moves out of the way.
But when you hit those massive wind tunnel speeds, the air literally smashes into the front of your tiny model car and compresses, packing tightly together and physically changing its density.
Exactly. And the real car, driving at 60 kilometers per hour, does not experience that compressibility at all.
So the test is completely invalid.
Completely. The general rule of thumb in aerodynamics is that the maximum tolerable threshold for treating air as incompressible is around Mach 0.3.
Anything faster than that, and the physics of your wind tunnel no longer match the physics of the highway. Your test is ruined.
Yep. You are testing a phenomenon that the real car will never actually experience.
So you are trapped in a physics paradox. You have to spin the wind tunnel up to 370 miles per hour to match the Reynolds number, but the moment you do that, you ruin the air density through compressibility. How on earth does an engineer solve this?
Well, you have two incredibly clever workarounds. The first option is to just completely abandon air as your testing medium.
Wait, really? What do you use instead?
Instead of putting the car model in a wind tunnel, you submerge it in water.
Ah, you put the aerodynamic car in a circulating water flume or a massive towing tank?
Yes. Because water has a vastly different density and a vastly different viscosity than air, the math completely shifts in your favor.
That is so smart.
If you run the Reynolds number equation using the properties of water instead of air, you find that to match the full-scale car, the water velocity over the scale model only needs to be 11.1 meters per second.
Only 11.1. That is roughly 25 miles per hour. That is incredibly manageable.
Very manageable. And water is essentially incompressible under these conditions, so you completely bypass the Mach number problem.
That is a brilliant hack. But let's say you are an aeronautical engineer and you really truly want to use air. You have to use a wind tunnel for some reason. What's the second option?
Your second option is to build a variable density wind tunnel.
Okay, what does that look like?
You take the entire wind tunnel facility and you encase it inside a massive, heavily reinforced steel shell. And then you crank up the atmospheric pressure inside that shell.
You literally pressurize the room.
Severely.
Yeah.
If you increase the pressure inside that wind tunnel to 10 atmospheres, meaning 10 times the normal pressure of the Earth's atmosphere at sea level, the density of the air increases proportionally.
Oh, I see the math now.
Because the air is now 10 times denser, you can equalize the Reynolds number on your tiny model without increasing the wind speed at all.
You get to keep the wind speed slow, avoiding the compressibility problem, but the sheer crushing density of the air gives you the dynamic similarity you need.
Exactly. It's an engineering marvel.
But imagine standing next to a wind tunnel that is pressurized to 10 atmospheres. The structural engineering required just to keep the building from exploding outward is staggering.
It is a massive, expensive undertaking, but necessary for accurate scaling.
Okay, so the Reynolds number dictates the balance of inertia versus viscosity. But there are other critical force ratios depending on what you are trying to build, right?
Absolutely. If your domain is naval architecture, so designing ships, boats, or harbor structures, your primary concern actually shifts away from the Reynolds number and toward the Froude number.
The Froude number. And what forces is that comparing?
The Froude number is the ratio of inertia force to gravity force.
Why does gravity suddenly take center stage when you are designing a boat? I mean, submarines use Reynolds. Why do surface ships use Froude?
Because a surface ship operates exactly at the interface of two vastly different fluids, water and air.
Ah, the surface.
Right. As the ship's hull pushes through the water, it physically displaces it upward into the air, creating a surface wave.
And gravity is the constant, relentless force trying to pull that wave back down to a flat, level surface.
Exactly. Therefore, the Froude number governs wave resistance, which is the massive amount of energy a ship loses just by pushing waves outward.
If you look at a massive commercial container ship, say 245 meters long, sailing across the Pacific at 28 knots, it is dragging an enormous wake behind it.
And if you were an engineer tasked with testing a 1 to 25 scale model of that container ship to optimize its hull shape, you cannot just drag it through a towing tank at random speed.
It's because the waves wouldn't match.
Right. Froude's law of similarity dictates the precise, mathematically exact towing velocity you must use so that the wave patterns generated by the tiny wooden model perfectly mimic the towering ocean waves generated by the real ship.
That's fascinating. Then we have the Weber number, which is a bit more niche but incredibly important for specific industries.
Very niche, yes. The Weber number is the ratio of inertia force to surface tension force.
When do engineers actually use that one?
You use this when you are analyzing how liquids behave when they are poured, how droplets form, or the behavior of very tiny capillary surface waves.
So things like fuel injectors in car engines.
Exactly. Or industrial sprayers, where breaking a fluid into a fine mist of tiny droplets is the entire goal of the design.
Makes sense. And finally, we arrive at the Mach number, named after the physicist Ernst Mach.
The legendary name in physics. The Mach number is the ratio of inertia force to elasticity, or compressibility force.
And the mathematical formula for that is surprisingly simple, isn't it?
It is. It is simply the velocity of the fluid divided by the local speed of sound in that fluid.
That's it.
That's it. But it is the absolute defining metric for high-speed aerodynamics.
Okay.
It dictates whether a flow regime is subsonic, sonic, supersonic, or hovering dangerously in the middle as transonic.
Right, like when you look at a Boeing 747 cruising at altitude, it is flying at roughly Mach 0.82, It is moving at 82% of the speed of sound.
Which is subsonic, yeah.
Subsonic, but it is pushing right up against that transonic boundary where the air over the top of the wings might actually locally accelerate past the speed of sound, creating shock waves.
Exactly. The local airflow can be supersonic even if the plane itself is subsonic.
And this leads us to one of the most fascinating historical detours in this whole subject. Ernst Mach, the man who gave his name to the Mach number, was a true visionary.
He was brilliant.
He used these exact principles of high-speed flow and compressibility to solve two bizarre, seemingly inexplicable mysteries in the late 19th century.
I love these historical examples.
If you are a history buff listening to this is where physics literally changes the historical record. Okay, mystery number one. The artillery bangs.
Yes, the dual explosion mystery.
Right. Back in the day, artillery crews and military observers noticed a truly bizarre acoustic phenomenon. When they fired a highly advanced, high-speed artillery projectile, an observer positioned far downrange, near the target, would hear two completely distinct, loud bangs.
One and then another shortly after.
Exactly. But if they fired an older, low-speed projectile from a mortar, the downrange observer would only hear one single bang.
The military establishment was totally mystified by this.
Completely baffled. Why did the fast shell make two explosion sounds and the slow shell only make one?
Mach tackled this, and he realized it was entirely a manifestation of the speed of sound.
How did he figure it out?
He realized that for the high-speed projectile, the very first bang the observer heard had absolutely nothing to do with the cannon firing.
It wasn't the muzzle blast at all.
Not at all. The first bang was the bow shock, a literal sonic boom generated by the physical nose of the projectile, violently tearing through the air and breaking the sound barrier.
Oh, wow. So because the projectile itself was traveling faster than the speed of sound, that compressed shockwave of air physically arrived at the observer's ear before the actual acoustic sound of the cannon's muzzle blast.
Exactly. The sound of the muzzle blast had to travel at the slower, normal speed of sound, arriving moments later as the second bang. The bullet literally outran its own gunshot.
It perfectly explains the opening scenario we talked about at the top of the show. The sound of the impact arrives before the sound of the trigger being pulled.
It's a perfect real-world example of the Mach number in action.
But the second mystery Mach solved is even wilder and much more gruesome. It takes place during the Franco-Prussian War.
Yes. A very dark but fascinating application of fluid dynamics.
The French infantry were equipped with a revolutionary new weapon called the chassepot rifle. It fired a bullet at an unprecedentedly high velocity for the era.
Unprecedented speed.
And the Prussian soldiers on the receiving end were suffering massive, devastating, crater-shaped wounds that looked nothing like standard bullet holes.
The trauma was so severe that the Prussian government was actually outraged.
Yeah, they formally accused the French military of committing war crimes, claiming the French were illegally stuffing the bullets with explosive charges that detonated on impact.
They firmly believed the bullets contained tiny bombs. They couldn't explain the trauma any other way.
But Ernst Mach investigated the ballistics, and he proved mathematically and physically that the French were not using explosives at all.
No explosives whatsoever.
The massive crater wounds were a pure, horrifying demonstration of fluid dynamics.
Because the chassepot bullet was moving at such extreme supersonic velocity, it was creating an intensely pressurized bow wave of highly compressed air violently pushed in front of the metal bullet.
The compressibility we talked about earlier.
Exactly. Mach proved that when air is compressed by sheer unadulterated speed, it becomes a physical weapon.
So it was this invisible wall of compressed air hitting the flesh a microsecond before the bullet itself that caused the explosive-style trauma.
The air itself acted as the explosive. It is a profound, terrifying realization about what fluid dynamics actually means in the physical world when things move fast enough.
That is just incredible. Okay, let's pull back from the battlefield. This perfectly sets up our second phase.
Transitioning to measurement.
Right. Let's say we have navigated the headache of scaling. We have our dynamically similar model. We have placed it in our 10-atmosphere pressurized wind tunnel or our giant water flume. How do we actually read what the fluid is doing?
This is a major engineering hurdle.
Because air is totally invisible. Water is entirely transparent. We cannot just stick a standard mechanical car speedometer out the window into the wind tunnel and expect it to tell us anything useful.
No, the wind would just blow right past it.
We have to invent tools that can measure the invisible.
This brings us to the ingenious tools of the trade. And engineers generally divide these measuring devices into two broad categories.
Okay, what are the two categories?
First, you have point measurement tools, which tell you the exact velocity of the fluid at one tiny specific spot in space.
It's like tracking a single particle.
Exactly.
Mhm.
And second, you have volume measurement tools, which tell you the massive overall flow rate of liquid moving through an entire system.
Let's start with measuring velocity at a single pinpoint spot. The absolute reigning champion of this is the pitot tube, right?
Without a doubt. If you look at the nose of any commercial airliner, you will see these little metal spikes sticking out. Those are pitot tubes.
Yes, specifically the pitot tube, like the classic National Physical Laboratory type mentioned in the text. It is a remarkably simple, completely mechanical, but profoundly brilliant device.
It really is. At its core, it consists of a small metal tube pointing directly straight ahead into the oncoming flow of fluid.
And as the air or water rams straight into the open front hole of that tube, it has nowhere to go. It hits a dead end.
Exactly. The fluid rams into the tube and is forced to come to a complete dead stop.
And in physics, when moving fluid stagnates like this, all of its kinetic energy, its speed, is instantly converted into pressure.
We call this the total pressure, or the stagnation pressure.
But just knowing that total pressure reading at the dead end of the tube isn't enough to calculate speed, right? Because what if the ambient environment is just highly pressurized to begin with, like deep underwater?
Right, you can't just take the raw number. You have to subtract the ambient background pressure to isolate the speed.
And that background pressure is called the static pressure, the pressure of the fluid just sitting there calmly.
The genius of the pitostatic tube is how it finds that background pressure. It has tiny, microscopic holes drilled into the side of the tube, perfectly perpendicular to the flow.
So the wind blows directly over these holes without ramming into them, allowing the instrument to measure the pure static pressure.
Exactly. So you have two pressure readings: the massive total pressure from the front hole and the calm static pressure from the side holes.
And by comparing the two, you extract the velocity.
Yes. The formula is a beautiful derivative of Bernoulli's equation. The velocity of the fluid equals the square root of 2 times the difference between the total and static pressure, completely divided by the density of the fluid.
You are literally taking the physical brute force pressure, pushing against a piece of metal, and mathematically converting it into speed.
It's brilliant. And because engineers love to iterate, there are some incredibly specialized variations of this simple tube.
Oh, yeah. Like if you were trying to measure a complex two-dimensional flow where you aren't exactly sure which way the wind is blowing, you use a cylinder-type tube, often called a yaometer.
The yaometer is fascinating. It's a cylinder with 2 pressure holes drilled at precise angles. You insert it into the flow, and you physically rotate the cylinder on its axis until the pressure reading from both holes is perfectly identical.
They balance perfectly.
Exactly. And the moment they balance, you know the cylinder is pointing perfectly dead center into the oncoming flow direction. It physically finds the wind for you.
There's also a 5-hole spherical pitot tube for mapping chaotic 3-dimensional flow directions.
Yes, for very complex flows.
And if an engineer needs to measure the velocity of the fluid right up against the solid boundary wall of a pipe or a car hood where the boundary layer gets microscopically thin, they use flattened total pressure tubes.
Right, they squash the opening down so it can fit in that tiny space.
Or they use surface pitot tubes that sit perfectly flush, integrated right into the wall itself, so they don't disturb the very flow they are trying to measure.
Now, all of those pitot variations rely on pressure. But the next tool on our list takes a completely different approach.
This one is wild.
The hot wire anemometer. It measures velocity by measuring temperature.
This is one of my absolute favorite concepts, and it brings me right back to food analogies.
Let's hear the food analogy.
Okay. Imagine you are sitting at a table with a bowl of scalding hot soup. You scoop up a spoonful, and you blow on it to cool it down.
A universal experience.
Right. The harder and faster you blow on the spoon, the more rapidly the soup loses its heat. The hot wire anemometer is exactly that, just weaponized with electricity.
That is precisely the underlying principle. The instrument consists of 2 tiny prongs, and suspended between them is an incredibly fine, almost microscopic wire.
Usually made of platinum or tungsten, right?
Yes. This tiny wire is heated electrically until it is quite hot. The probe is then placed directly into the rushing wind or flowing liquid.
As the cold fluid rushes past the hot wire, it forcefully strips the heat away, cooling the metal down.
And here's the trick of physics we exploit. When the temperature of a specific metal wire changes, Its electrical resistance, its ability to let electricity flow through it, changes proportionally.
So as the wire gets colder, the resistance drops.
Exactly. So you aren't actually measuring the wind physically pushing against a tube. You are measuring the electrical resistance of this tiny wire, which tells you exactly how much heat was stripped away, which tells you exactly how fast the fluid is moving.
But, I mean, early versions of this had a problem, didn't they?
They did. Thermal lag.
Right, because if the wind speeds up, the wire cools down. But then it takes a fraction of a second for the wire to heat back up when the wind slows down again.
Yes. This is called thermal inertia, and it makes the readings lag behind reality. To solve this, modern engineers developed the constant temperature anemometer, or CTA,
How does the CTA fix the lag?
by not letting the temperature drop at all.
Wait, what?
The CTA features a highly advanced, ultra-fast electronic feedback circuit. The instant the wing speeds up and begins to cool the wire even a fraction of a degree, the circuit instantly floods the wire with higher electrical voltage.
Oh, forcing the temperature to remain perfectly steady.
Exactly, so the temperature never changes. The instrument measures how much electrical power it has to violently pump into the wire just to maintain that constant heat.
Wow. And because the wire never physically changes temperature, thermal inertia is virtually eliminated.
It reacts instantaneously to changes in wind speed. These CTA instruments are so fast, they have an incredible frequency response. They can measure turbulent, chaotic fluctuations in the wind up to 100 kilohertz.
That is 100,000 distinct velocity measurements every single second. You can map the tiniest, most violent microeddies in a turbulent storm with that.
It's an incredibly sensitive instrument.
But if we want to talk about the absolute pinnacle of high-tech measurement, we have to talk about lasers. The laser Doppler anemometer literally feels like it was pulled straight out of science fiction. You are pointing laser beams at dust.
It is an incredibly elegant, non-intrusive application of physics. It relies entirely on the Doppler effect.
Okay, let's explain the Doppler effect. If you are driving down the street and an ambulance is speeding towards you with its sirens blaring, you hear the Doppler effect.
The classic example.
As the ambulance races toward you, it is chasing its own sound waves, compressing them, making the pitch of the siren sound higher. As it races past you and drives away, the sound waves are stretched out behind it, and the pitch noticeably drops.
Exactly. The frequency of the wave changes based on the speed of the object emitting it. But with the laser Doppler anemometer, instead of using acoustic sound waves, we're using the electromagnetic waves of light, a highly focused, coherent laser beam.
To make this work, the fluid we are studying has to be seeded with tiny, microscopic tracer particles. Think of incredibly fine dust or microscopic oil droplets that are so small they perfectly follow every twist and turn of the fluid flow.
Yes, the tracer particles are key. When you fire the laser beam into the transparent fluid, the light eventually strikes one of these microscopic particles moving with the flow.
And as the laser light bounces or scatters off that moving particle, the frequency of the scattered light changes based on how fast the particle is moving, just like the ambulance siren.
The instrument then collects that scattered light. By mathematically measuring the microscopic difference in frequency between the original pure laser beam and the altered scattered light, you calculate the exact absolute velocity of the particle and therefore the fluid.
The math behind this is wild. The velocity of the flow equals the wavelength of the laser, multiplied by the Doppler frequency difference, completely divided by 2 times the sine of the angle of the intersecting beams.
It's a beautiful equation.
Yeah.
You are measuring the speed of microscopic dust by analyzing how it bends laser light.
And engineers use several different optical setups to achieve this, right?
They do. Primarily the reference beam method, the single beam method, and the interference fringe method.
The fringe method is especially cool.
It is. In the fringe method, you actually split the laser into 2 beams and cross them. Where they intersect, they create microscopic alternating bands of light and dark fringes.
Like a barcode of light.
Exactly. As a particle flies through these bright and dark bands, it flashes light back at the sensor. The speed of the flashing tells you the speed of the particle.
The massive advantage here is that it is totally non-intrusive. Unlike a metal pitot tube or a delicate hot wire, you are not plunging a physical object into the flow that might disrupt the delicate aerodynamics you are trying to measure. You are just shining light through a glass window.
It is the perfect tool for highly sensitive, highly turbulent flows. Now, everything we just discussed is for measuring velocity at one specific pinpoint location.
Right. Point measurement.
But what if you don't care about a single point? What if you're an engineer managing a massive oil pipeline or a municipal water treatment plant, and you need to know the massive overall volume flow rate?
You need to know exactly how many thousands of gallons or cubic meters are moving through the entire pipe every minute.
Exactly. You don't need a point velocity. You need a flow meter.
And looking at the options, the most common rugged industrial method is forcing the fluid to squeeze through a restriction. You purposefully put a metallic obstacle inside the pipe.
Yes. The simplest version of this is the orifice plate. Imagine a solid, flat, circular steel plate with a precise hole drilled right in the center. You insert this plate directly into the cross-section of the pipe.
So as the massive volume of fluid hits this barrier, it is forced to squeeze through that smaller central hole.
And according to Bernoulli's principle of fluid dynamics, whenever a fluid is forced to accelerate through a narrower space, its pressure drops proportionally.
Right. So by placing a pressure sensor just upstream of the metal plate and another pressure sensor just downstream of the plate, you can measure the exact pressure difference.
Yes. The total volume flow rate of the fluid is directly proportional to the square root of that pressure difference.
Yeah.
It is a highly reliable, mathematically sound way to measure massive volumes.
But there is a catch, isn't there?
There is always a catch.
If you just shove a flat plate into a high-pressure water main, the fluid violently smashes into the flat surface, squeezes through the hole, and then violently expands on the other side. It creates massive chaotic turbulence.
And turbulence is just wasted energy. That violent expansion behind the orifice plate results in a permanent pressure loss in your pipeline system.
Which is bad.
Very bad. If you are managing a pipeline stretching hundreds of miles, every ounce of lost pressure means your massive industrial pumps have to work harder, burning more electricity and costing massive amounts of money.
So how do you measure the flow restriction without creating the chaotic, expensive turbulence?
You use ISA 1932 nozzles, or much more commonly, venturi tubes.
Venturi tubes, how are they different?
Instead of a harsh flat plate, a venturi tube is a beautifully machined piece of pipe that smoothly, gradually tapers down to a narrow throat and then gently, gradually expands back out to the full diameter of the pipe.
So it guides the water instead of blocking it.
Yes. The physical principles are identical to the orifice plate. The fluid accelerates in the narrow throat, the pressure drops, and you measure the difference.
But without the violence.
Exactly. The flow coefficients differ slightly in the math, but the massive advantage is that a venturi tube has a remarkably low permanent flow loss. The gentle curves prevent the violent turbulence from forming, saving massive amounts of pumping energy.
That makes a lot of sense. Let's shift away from pressure-based meters to area flow meters, specifically rotameters.
Rotameters were fantastic.
If you have ever been in a hospital room with an oxygen line on the wall or a chemistry laboratory, you've almost certainly seen a rotameter. It is the vertical, transparent glass or plastic tube with a little floating bob inside it.
The rotameter is a brilliant tactile balancing act of physical forces. The fluid, whether it is oxygen gas or liquid water, flows vertically upward from the bottom of the tube to the top.
Right.
As the fluid hits the solid little float sitting at the bottom, it creates upward pressure drag and friction drag. The rushing fluid literally tries to push the float up into the air.
But gravity is constantly pulling the heavy float back down.
Exactly. The float rises upward until the pushing force of the fluid exactly balances the downward weight of the float, minus whatever natural buoyancy the float has.
Now, if the glass tube was perfectly straight like a straw, the float would either shoot all the way to the top or sit at the bottom.
Right. There would be no graduation.
The genius of the rotameter is that the glass tube is tapered. It is narrower at the bottom and wider at the top.
So as the float is pushed higher up the tube, the annular gap, the empty space between the float and the glass wall, gets wider and wider.
Which means more and more fluid can slip past the float.
Yes. Because of this expanding area, the upward drag force decreases the higher the float goes. Eventually, the float finds an exact stable resting height where the drag perfectly matches the weight.
That physical resting height is directly proportional to the flow rate. You just look at the float, read the printed number on the side of the glass tube next to it, and you know exactly how much fluid is moving.
It is so beautifully visual.
But let's say we were dealing with something incredibly thick, sticky, and valuable, like crude oil or heavy syrup. You don't want to rely on balancing a tiny float.
No, a float wouldn't work at all there.
Right. You use positive displacement meters, like oval gear meters or roots type meters. These feel much more like heavy machinery.
Because they are. Positive displacement meters do not try to infer the flow rate by measuring pressure drops or drag forces.
How do they work then?
They literally physically trap a very specific known volume of fluid in a mechanical chamber, transport it from the inlet to the outlet, and dump it out.
It is exactly like a revolving door at the entrance of a busy hotel.
That's a great way to picture it. Every time the revolving door turns one complete circle, you know exactly 4 people walked inside.
Precisely. In an oval gear meter, 2 interlocking oval-shaped gears rotate as the fluid pushes against them. Every time those gears complete one full revolution, a mathematically exact pocket of fluid has been moved through the pipe.
So to calculate the massive flow rate, you don't measure pressure, you simply hook up a sensor to count the physical revolutions of the gears.
And closely related to that is the turbine flow meter. You just drop a multi-bladed propeller turbine into the middle of the pipe. The rushing water catches the angled blades and spins the turbine.
The faster the water, the faster it spins.
But how do you accurately count the speed of a spinning blade inside a high-pressure, sealed steel pipe without leaking water everywhere?
You use electromagnetism.
Of course.
You embed a small, powerful magnet into the tip of one of the turbine blades, and on the outside of the pipe, completely sealed away from the fluid, you mount a magnetic pickup coil.
Every single time that magnetized blade spins past the coil, it generates a tiny, microscopic electrical pulse. A computer simply counts the frequency of those electrical pulses. More pulses equals more flow.
Which perfectly transitions us into what I consider absolute physics magic, magnetic flow meters.
I want you to explain this slowly, because when I first read how this works, it sounded entirely impossible.
It does sound like magic. It relies on Michael Faraday's law of electromagnetic induction.
Oh, okay, Faraday's law.
Faraday discovered in the 19th century that if you take a conductive material like a copper wire and you physically move it through a magnetic field, the invisible magnetic forces will induce a voltage, an electromotive force, directly inside the wire.
It is how every electrical generator on Earth works.
Exactly. But a magnetic flow meter doesn't have any moving copper wires in it.
No, it doesn't. So how does it generate voltage?
In a magnetic flow meter, the pipe itself is lined with a non-conducting material, like rubber or Teflon. But the fluid flowing through the pipe, say municipal wastewater, or acidic chemicals or liquid metal, is electrically conductive.
Wait, so the fluid itself acts as the moving wire?
Yes. The river of wastewater is the wire.
That is insane.
The flow meter uses massive coils to project a strong, constant magnetic field straight across the diameter of the pipe. As the conductive fluid flows rapidly through this invisible magnetic field, the physics of Faraday's law activate.
An electromotive force, a distinct electrical voltage, is generated directly within the flowing water.
And how do you capture that voltage? The meter has 2 small metallic electrodes mounted perfectly flush against the inside wall of the pipe, directly in contact with the water. These electrodes detect the voltage.
And the mathematical formula governing this is pure elegance. The voltage generated equals the magnetic flux density, multiplied by the diameter of the pipe, multiplied by the mean velocity of the flow.
Since the magnetic field and the pipe diameter are constant, the voltage you measure is perfectly linearly proportional to how fast the water is moving.
And what is the massive, world-changing engineering advantage of doing it this way?
0 pressure loss. Absolutely 0.
That's huge. There's no orifice plate violently squeezing the water. There's no heavy turbine blade sitting in the way waiting to get jammed.
The pipe is a completely open, hollow, unobstructed tube. You're measuring the massive rush of millions of gallons of water purely by feeling its invisible electromagnetic pulse.
It is the ultimate tool for handling slurries, heavy sewage, or any fluid thick with solid debris that would instantly shatter or jam a mechanical turbine.
It really is.
That is incredible. Next, we have ultrasonic flow meters. These sound incredibly high-tech, but the concept is actually very straightforward.
It is. The meter sends acoustic sound pulses diagonally across the diameter of the pipe.
It fires one high-frequency sound wave downstream, completely traveling with the flow of the water, and it fires a second sound wave upstream, fighting against the flow of the water.
Because the entire body of water is physically moving, the sound wave traveling downstream is carried along and arrives at the opposite sensor slightly faster than normal.
Conversely, the sound wave fighting its way upstream is slowed down.
It is exactly like swimming with a river current versus swimming against it.
The flow meter's internal computer measures the microscopic fraction of a millisecond time difference between the two arrivals. That minute time delta tells you exactly how fast the fluid is moving.
The major advantage here is that ultrasonic meters can measure non-conducting fluids like ultra-pure hydrocarbons or distilled water, where the magnetic flow meter would completely fail.
Because there's no conductivity.
Right. However, they are highly complex and notoriously expensive.
And we have one last major pipe meter, the vortex shedding flow meter. This takes us right back to the deep aerodynamics we discussed earlier.
Yes, back to vortices.
Imagine an island in the middle of a fast-moving ocean current. As the water flows around the island, it doesn't just reform cleanly behind it. It creates alternating swirling whirlpools that detach from the island and trail behind it in a very specific alternating zipper pattern.
That beautiful repeating pattern of swirling eddies is called a Kármán vortex street. You can actually see them in satellite photos of clouds parting around mountain peaks.
It's mesmerizing to look at. A vortex shedding meter intentionally places a non-aerodynamic obstacle, usually a blunt cylinder, directly into the center of the pipe to forcefully create these alternating vortices.
The text mentions a dimensionless number controlling this, the Strohel number.
Yes, the Strohel number.
The Strohel number governs oscillating flow mechanisms. And for a standard cylinder, the Strohel number remains almost perfectly constant at approximately 0.2 over a massive range of different fluid velocities.
Because that number is constant, it dictates that the frequency at which these swirling vortices detach from the cylinder is completely directly proportional to the velocity of the fluid.
The formula is beautifully simple. Velocity equals the vortex shedding frequency multiplied by the diameter of the cylinder, completely divided by 0.2.
So the meter just contains a tiny sensor that detects the physical pulsing of the vortices hitting it, like a heartbeat. It counts the pulses to count the flow.
The engineering text also touches briefly on specialized applications, like fluidic oscillators, which utilize complex wall attachment feedback loops to create a rapidly oscillating jet of fluid whose frequency tracks the flow rate.
And for massive open-channel flows like monitoring an entire river or a concrete aqueduct, engineers use weirs.
Weirs are essentially controlled waterfalls. You build a barrier across the river, let the water crest over it, and measure how high the water gets.
Yes, there are triangular, rectangular, and full-width weirs. By measuring the physical height of the waterhead as it spills over the notch, engineers use specific British standard formulas to calculate the massive volumetric flow of the entire river.
It is an absolutely staggering array of physical tools, from counting interlocking gears, to bouncing laser beams off microscopic dust, to measuring the electromagnetic voltage of a moving river, to counting the heartbeat of a vortex street. Engineers have found a way to measure fluid in almost every conceivable physical state.
It is a triumph of applied physics. But all of these tools, as incredible as they are reactionary. They are designed to measure what a fluid is already doing.
Which leads us to the final and absolutely most profound phase of this masterclass.
We can scale our models, we can measure the air in our tunnels, but what happens before any of that? How does an aeronautical engineer mathematically predict how a fluid will behave before they ever build a single piece of metal?
That is the holy grail of fluid dynamics, to predict the chaotic, swirling nature of reality using only a pencil and paper.
And to achieve this, the early pioneers of engineering had to make a massive, counterintuitive leap. They had to invent a perfect, entirely impossible fluid.
Welcome to the realm of ideal fluid flow and the breathtaking math of flight.
Let's go back to the Reynolds number, the battle between forward inertia and sticky viscosity. We established that for aircraft flying at high speeds, or ships moving through water, the Reynolds number is incredibly, massively high.
Right. The forward inertia absolutely dominates the viscosity.
And because the inertia is so dominant, a strange physical phenomenon occurs. The effects of the fluid's sticky viscosity become entirely confined to an unimaginably thin layer of air right against the solid surface of the object.
We call that the boundary layer.
And outside of that microscopically thin boundary layer, the vast, overwhelming majority of the air flowing over the giant wing of an airplane simply ignores viscosity entirely. It flows as if the stickiness doesn't exist.
So mathematically, engineers make a terrifyingly bold, simplifying assumption. They say, let's treat the entire ocean of air as an ideal fluid.
An ideal fluid is defined by two impossible conditions. First, it is perfectly inviscid, meaning it has absolutely zero viscosity, zero internal friction.
And second, it is irrotational, meaning there is no swirling vorticity, no microscopic whirlpools twisting the fluid particles. The particles only glide smoothly.
But wait, if you just drop viscosity, one of the fundamental properties of the universe, from your math, isn't that just cheating? Doesn't the math break?
It sounds like cheating, but it's actually a masterful stroke of reduction. By dropping the viscosity, we get to discard the incredibly brutal, unsolvable, viscous terms of the Navier-Stokes equations.
Which are famously impossible to solve analytically.
Exactly. We can replace them with Euler's equations of motion. And the profound beauty of this ideal fluid assumption is that it cleanly splits the physics into two manageable independent parts.
Explain how it splits the physics.
Well, the momentum equation is now solely responsible for determining the physical pressure distribution. But the actual geometric shape of the flow, the beautiful curving pathways the air takes as it flows around the wing, is completely and entirely dictated by the continuity equation, governed by the geometry of the solid object itself.
Okay, I need to visualize this because we are entering pure geometry now. The concepts here are the velocity potential and the stream function. I try to picture this like a vast, perfectly planned city grid like Manhattan.
I like this visualization. Walk me through it.
Imagine the fluid flow as a massive city grid. The streamlines, what the math calls the stream function, are the wide avenues. They dictate exactly where the traffic or the fluid particles physically flow. A particle cannot cross a streamline, it must flow perfectly down the avenue.
Okay, that tracks.
Now, intersecting those avenues are the cross streets. Those are the equipotential lines, what the math calls the velocity potential.
And here is where the strict rules of our ideal fluid create magic. Because we assume the flow is perfectly irrotational, we mathematically prove that a velocity potential, which we denote with the Greek letter phi, must exist.
And because we assume the flow is incompressible, we mathematically prove that a stream function psi must exist.
And the profound mathematical reality that governs this entire system is that both phi and psi perfectly satisfy Laplace's equation.
And when you map out Laplace's equation onto our theoretical city grid, a beautiful geometric law emerges.
Tell me.
At every single microscopic point on that massive map, wherever an avenue streamline intersects with a cross-street equipotential line, they cross at exact, perfect 90-degree right angles.
Always, without exception, they form an orthogonal net. You have constructed a perfect mathematical grid of fluid flow.
But here's where the mathematics take an even wilder, almost spiritual leap. This is where we transition into the true beauty of potential flow. To manipulate this grid, we use complex variables.
Complex numbers. We're talking about imaginary numbers.
Yes. We define a single, unified, complex variable, which we call z. And z equals the x-coordinate plus the imaginary unit I multiplied by the e-coordinate.
For anyone who needs a quick refresher, the imaginary unit I is the square root of -1.
A number that literally cannot exist in standard arithmetic because no real number multiplied by itself can be negative. But it creates a second vertical dimension to our number line.
Exactly. It creates a two-dimensional mathematical plane. And in high-level mathematics, any regular function of a complex variable automatically satisfies an incredibly strict set of rules known as the Cauchy-Riemann equations.
But why does an aeronautical engineer trying to build a physical metal wing care about a rule for imaginary numbers?
Because of an unbelievable coincidence in the structure of the universe.
I love when that happens.
If a complex math function satisfies the Cauchy-Riemann equations, its real part automatically perfectly obeys every single rule for our velocity potential, phi, and its imaginary part automatically perfectly obeys every single rule for our stream function size.
Let me make sure I am grasping the magnitude of this. You can literally just write down a random algebraic function using an imaginary number, differentiate it on a chalkboard, and it will perfectly map out the real physical movement of invisible air and water.
Yes, the imaginary math seamlessly translates into physical fluid mechanics. We call this unified mathematical tool the complex potential.
And by manipulating this complex potential, theoretical engineers can build predictive models of any flow pattern imaginable.
To do this, we use a set of basic mathematical building blocks. Think of them as the fundamental Lego bricks of fluid dynamics.
Okay, let's open up the Lego box. If we are building a theoretical flow from scratch, what is the absolute simplest mathematical brick we can start with?
Block number 1, parallel flow. This represents a massive, uniform wind blowing steadily in one straight direction.
The mathematics are wonderfully simple. The complex potential is simply the uniform forward velocity, u, multiplied by our complex variable z.
The streamlines are perfectly straight, horizontal avenues. The equipotential lines are perfectly straight, vertical cross streets.
That is our blank canvas. What is block number 2?
Block number 2 is the source and the sink. Imagine a mathematical pinpoint in space where fluid miraculously appears out of nothing, flowing equally outward in every possible direction. That is a source.
The opposite is a sink, a pinpoint where fluid drains endlessly out of the universe.
The complex potential for this involves the natural logarithm of z. If you map it, the equipotential cross streets are perfectly concentric circles expanding outward.
The streamline avenues are straight, radial lines shooting outward from the center, exactly like the metal spokes of a bicycle wheel.
Okay, we have wind and we have bursting sources. What is block number 3?
Block number 3, the free vortex. Imagine fluid spinning in perfect, infinite concentric circles around a central origin point. It is a mathematical whirlpool.
The velocity of the fluid is incredibly high near the dead center and drops off exponentially the further out you travel. This block introduces the vital concept of circulation.
Okay, we have our basic Lego bricks, parallel flow, sources and sinks, and free vortices. Now we start synthesizing physical reality.
Because Laplace's equation is linear, you can literally just take the mathematical equations for these different blocks and add them together to build complex shapes.
Let's build a physical object. Take a source and a sink and place them on our mathematical grid, separated by a distance.
Now mathematically move them closer and closer together, decreasing the distance while increasing their strength, until they are infinitely close to one another, practically overlapping.
You have just forged a new advanced building block called a doublet.
Okay, I have an infinitely dense doublet in my hand.
Now take that doublet and drop it right into the middle of our first block, the uniform parallel flow wind. Mathematically, you just add the equation of the doublet to the equation of the parallel flow.
And when you map the resulting streamlines, the math miraculously parts the uniform line perfectly around a solid physical cylinder.
It does. It is breathtaking to see on paper. The mathematical streamlines part around the microscopic origin exactly, flawlessly as real air parts around a physical steel pipe in a wind tunnel.
Using this equation, you can perfectly calculate the exact stagnation points at the absolute front and absolute rear of the cylinder, where the fluid smashes into it and its velocity drops to zero.
You can calculate the highest, fastest velocity points where the air accelerates over the top and bottom, all derived purely from adding a theoretical doublet to a uniform wind.
Okay, this is beautiful. The geometry is elegant.
Yeah.
But here is the ultimate practical pushback.
Amy.
Airplanes do not fly on giant, blunt, circular cylinders. They fly on highly specialized, flat, asymmetrical, teardrop-shaped airfoils.
That is a very valid point.
How does perfectly calculating the wind around a circular pipe help Boeing or Airbus get a massive jetliner off the ground?
This is the masterstroke of fluid dynamics. This is where abstract mathematical genius meets the gritty reality of engineering. We use a mind-bending technique called conformal mapping.
Conformal mapping.
Yes.
Yeah.
Specifically, an equation known as Joukowski's transformation. It is essentially a mathematical warp drive.
Oh, warp drive.
You take the entire complex grid, the original Z-plane, where we just build our perfect symmetrical flow around a cylinder, and you mathematically warp, stretch, and map that entire space onto a brand new dimensional plane.
The Joukowski transformation formula itself is incredibly compact. The new warped variable, zeta, equals the old variable z plus a constant squared divided by z.
If I apply that warp drive to our cylinder, what happens to it?
If you take a standard perfect circle centered dead on the mathematical origin, Joukowski's transformation violently crushes it, flattening the circle completely into a single, flat, two-dimensional plate.
But, and this is the absolute genius of the technique, if you offset the original circle just a little bit, sliding its center slightly up and slightly left away from the origin before you apply the mathematical warp.
The transformation stretches, pulls, and warps the perfect cylinder into the exact, unmistakable, asymmetrical teardrop shape of an airplane wing.
An airfoil, yes.
Yeah.
And here is the true power of conformal mapping. It doesn't just warp the solid shape of the wing, it warps the entire invisible grid of the fluid.
The streamline avenues and the equipotential cross streets perfectly elastically bend and stretch along with the solid shape, all while strictly maintaining their perfect 90-degree intersections.
The theoretical flow pattern around a simple cylinder is flawlessly translated into the highly complex flow pattern around an aircraft wing.
It is mathematical alchemy. You turn a pipe into an airplane wing.
Yeah.
But there is one final critical physics glitch. Because nature hates a paradox, we have to talk about the Kuta condition.
We do. if you just naively map the cylinder flow directly to the wing shape using the Joukowsky transformation, the math dictates something physically violently impossible.
And airfoil, by design, has a sharp, tapered trailing edge at the back.
The pure, unmodified mathematical mapping demands that the air flowing under the bottom of the wing has to whip around that razor-sharp trailing edge, curling up to the top at an infinite velocity.
And nature absolutely, categorically forbids infinite velocity.
It does. In the real world, nature resolves this impossible paradox through viscosity, the stickiness of the air tearing and creating turbulence at the edge. But remember, we assumed our ideal fluid has zero viscosity.
So mathematically, to force our perfect theoretical fluid to obey the harsh rules of physical reality, we manually introduce an overriding law called the Coulomb condition.
Which states what?
The Coulomb condition simply states that the sharp trailing edge of the wing must be a stagnation point. The air flowing over the top of the wing and the air flowing under the bottom of the wing must meet and leave the trailing edge smoothly, beautifully at the exact same time without ever whipping around the sharp corner.
But how do we physically force the mathematical equations to obey the Coulomb condition? How do we stop the infinite velocity?
We reach back into our box of mathematical Lego bricks. We take our third block, the free vortex, circulation.
Before we map the cylinder to the wing, we mathematically force a highly specific, precisely calculated amount of spinning circulation into the cylinder's equation. We basically add a spinning whirlpool to the flow.
And this forced circulation, mathematically required purely to stop the impossible infinite velocity at the trailing edge,
Is literally the force that generates lift.
the circulation accelerates the air over the top of the wing, lowering the pressure, and decelerates the air under the wing, raising the pressure. The high pressure pushes up into the low pressure. Lift is born.
By adding a spinning vortex to a cylinder and using imaginary numbers to stretch that cylinder into a teardrop, we unlocked the mathematical secret to human flight.
It is, without exaggeration, one of the greatest intellectual triumphs in the history of theoretical engineering. You start with the absurd assumption of an impossible frictionless fluid.
You calculate it using imaginary numbers that possess the square root of -1.
You warp dimensional space using conformal mapping, and you end up with an elegant equation that perfectly, flawlessly predicts the massive real-world physical lift required to wrench a 400-ton aircraft off the runway and carry it safely across an ocean.
It leaves you with such a profound, almost unsettling, lingering thought. Look at the journey of this masterclass.
We covered so much ground.
We started this deep dive with very physical, tangible, gritty things. We talked about dragging wooden model ships through massive water-towing tanks. We talked about building heavily reinforced wind tunnels pressurized to 10 atmospheres.
We talked about firing sonic boom-inducing artillery shells and shooting actual lasers into water to bounce off microscopic dust particles. Immensely physical, real-world interactions.
And yet we ended the journey entirely in the realm of pure, formless, abstract mathematics.
Exactly. We ended up relying on imaginary numbers that we literally invented, which cannot be measured on any physical ruler or scale in the universe, to perfectly, absolutely predict the massive, brute force physical forces that dictate our reality.
It really leaves you staring into the void, wondering, does mathematics simply describe the universe we live in as a convenient tool? Or is the physical universe, at its most fundamental, invisible level, actually made of mathematics?
That is the ultimate question. That is the paradox that keeps theoretical physicists staring at the ceiling at night.
It's certainly going to keep me awake tonight looking at the ceiling. That concludes our masterclass on the invisible forces that move the world. If you haven't already, give us a like and follow, and please leave us a comment if you enjoy the podcast. We love to hear from the folks who make this possible.